Okay, good afternoon again. Now we have discussed diodes and voltage regulate applications also. Next one we have to discuss is that transistors. Okay. You know that how to combine P-type and N-type semiconductor materials, and after that, you know that what will happen there. Okay, when we combine P-type and N-type semiconductor, it's PN junctions, junction diode. Okay. Now we can bring another part. Now we have only single junction. Now we can bring another N-type or P-type semiconductor part here. And we can make the second junction. Okay. Then this is another P. Then this is the one way we can do it, or maybe we can bring another N-type semiconductor block here, making another junction. Okay. But anyway, here we have PNP structure, and here we have NPN structure. But anyway, for these three parts, we can have three connections. Here also we can have three connections for this P-type, N-type, different type of semiconductor blocks. Then you can see here we have one junction and another junction. Here also we have two PN junctions. Okay. Then because of that, these two arrangements, now we have two type of three-terminal devices. These three-terminal devices we can call these are transistors. Okay, so this is coming something like that. This trans resistor. That's how this name is coming out. Anyway, that we can have it. We can have this one and this arrangement. Hereafter, we can have a different symbol to show this one without drawing this PNP and NPN structure here. We can have symbol to indicate these three terminals. This one, this is base terminal, and this is collector terminal, and this may be emitter. Emitter, this one collector, and this is base. Okay, here this PNP ones. This is base, collector, and emitter. This one, the arrow head is going away. This is base, collector, emitter. Now we have two different type of three-terminal devices, but you may assume that depending on the PNP structure, we have again two PN junctions, but situation or maybe the characteristics or maybe the function wise, it may be they will have opposite characteristics. They will have opposite functions depending on the structure, because one is NPN, the other one is PN. Okay, now if you consider this structure, now my simple question is this: shall we take this one? Okay. Now this is NPN transistor. Okay, I'll put a battery like this. What do you think? This is positive terminal, and this is PN junction, and this is PN junction. So this path, here we have one PN junction, here we have one PN junction. Through these two PN junctions, can we send a current like this? Can we expect a current? In other words, what we have done is we have connected a battery like this. And expecting a current to this path. Collector to emitter current. Is it possible to send this type of current? No, it's not possible. But we can send a current through this path. How? We can send a current through this path. And if you do this, and if we have this connection, and this is the transistor, and we have applied, for the moment, I put a resistor for the protection of the transistor, and we have applied a battery like this. But there is no current flow through this collector to emitter. External current is not there. But if you want to do that one, the simple way we have to do, but this is base terminal. This base to emitter, we have a junction. This base to emitter, we have a junction. What type of junction is this? It's a PN junction. And which part is the positive terminal? Base terminal. That will be the anode. If you consider this PN junction, if you consider this PN junction, and this is the anode terminal, this is the anode terminal, and this will be the cathode terminal. Okay, then if you want to forward bias this PN junction, what type of voltage we have to provide? Positive voltage to which pin? Base pin. The P-type semiconductor part should be positive, and N-type semiconductor part should be negative. Okay, with that, we can apply the type of voltage here. It may be variable one. Okay, then when you increase this voltage over 0.7 voltage, if you apply this one, then you can forward bias this emitter-based junction. This base to emitter junction, you can forward bias when you apply 0.7 voltage or more from this V2 battery. Is it okay? Okay. If you apply like this emitter-based junction will be forward biased. When you forward bias this junction, at that time, okay, that is the amazing characteristic of this transistor. At that time, you can see in the external path from collector to emitter, there is current going through this path. Okay. Did you understand this simple one? Initially, we tried to send the current from collector to emitter through the transistor, putting an external battery. But we can't see external current. Why? Inside that structure, we have two PN junction in opposite directions. Then how can we send the current? Well, first diode, first junction is reverse bias. Then it's not possible to send because that emitter to base junction, sorry, the first PN junction will be reverse bias. Because of that, we cannot send the current through collector to emitter. But when you have this setup initiated, and we'll have the other type of setup to the other terminal, then we'll try to forward bias base to emitter junction. When we forward bias this base to emitter junction, that means that we turn on this emitter-based junction. When we turn on this emitter-based junction, suddenly you can see in the external path, I current is there going towards collector and going through the transistor to the emitter. At that time, we can see another current is coming from this side. Then again, this is current. Because of that, this is the base current. We have connected to this terminal to the base. Then we say this is base current. And we connected this terminal to the collector. Then we say this is collector current. Okay. That is the simple behavior. That is the simple functionality of this transistor. Okay. Again, I'll draw it in detail. Now what we have done here, we have this transistor. And in this circuit, we have applied a certain voltage to this one. And after that, we applied another voltage to this one. It's variable one. V2. And this is resistor. This is 0 volts. This is plus V1. Okay. Here we have battery. Okay, I'll draw that way also, same way. Okay, now this is the setup. At that time, you can see this is collector current. We name it as IC. And this is base current. We name it as IB. And here it may be current going away from the emitter terminal. Then we say it's IE. At that time, we have this voltage. What is this voltage? VPE, emitter to base voltage. And after that, we have this voltage also. What is this? This is collector to emitter voltage, VCE. Okay. Here what we have done. Here what we have done. I'll take this one down. What we have done. First one, we forward bias. base emitter junction. Okay. We forward bias base, we providing positive voltage to the base terminal. This base terminal. This is base, collector, emitter, to providing positive voltage with respect to emitter terminal. We forward bias this base emitter junction. And you can see here V2 is a low voltage with compared to this one, with compared to this V1 voltage. Here V1 is larger than V2. Because of that, at V2 you can see less voltage than collector terminal. At base terminal we have less voltage than collector terminal, but what is that? Collector terminal is N-type semiconductor. Base terminal is P-type semiconductor. Then when you provide higher voltage than base terminal to this collector base junction, what will happen? Now, according to the setup, we reverse bias base to collect charge. But when you do this one, when you do this forward bias base to emitter junction, reverse bias base to collector junction, amazingly you can see suddenly the external path current is going towards the emitter terminal through the transistor. You can consider now we have turned on this device. Having this setup, you can see there is an external current going through the transistor and we can complete the path. Then we can consider we have switched on, we have turned on the transistor. Then to turn on a transistor, there are two requirements. Whatever the way, in whatever the application, to take the whatever the functionality from the transistor, first we have to turn on the transistor. How to turn on the transistor? Two conditions must be satisfied. What are the two conditions? To turn on the transistor, okay, to turn on the transistor, remember this, to turn on transistor. These two conditions must be satisfied. What is first condition? Base to emitter junction should be forward biased and base to collector junction should be reverse. Remember this. In whatever the way, you can check that these two conditions are there, then definitely this transistor can be turned on. Okay. Is it clear? Now with that, we have several parameters. We have several things came into the picture. What are those things? We have different currents, that is base current, collector current, and emitter, and two different voltages, base to emitter voltage and collector to emitter voltage. Okay. In addition to that, we say this one, the supply voltage. The supply voltage, this one. We name this voltage. Why? This is the collector terminal is connected to this voltage. Because of that, we say this is voltage collector terminal. This is VCC. Okay. And this VCC. This one. But this one is external voltage we are providing. But these 5 parameters are involving in the transistor. Earlier with the diode, we had only 2 things, forward voltage and forward current, VF and IF. But here we have 3 currents and 2 voltages. Is it okay? Any question? Okay, now shall we draw different graphs to understand the functionality of this one? Okay. What type of graphs that already you can draw? What type of things you can all? What is the first one? You can draw a graph between VBE and IB. What is that? VBE and IB. Already, do we know that one? What is that VBE? VBE is the voltage across base to emitter junction. That base to emitter junction is what? That is a diode. Base to emitter junction, if you consider that without considering collector, base to emitter junction is a diode. Is it clear? Then when you provide base to emitter junction 0.7 volts voltage, then it will be forward biased. Then because of this forward voltage, the forward current will be there. Then can we draw a graph? Can we draw a VI characteristic curve for this base to emitter junction? Yes, we already know about that. Okay. Considering this one, we can draw a characteristic curve for this. This is VBE and this is IB. Okay. What is that? How can we draw it? After 0.7 volts, it starts conducting like this. Normally this VBE, this one may be in volts and this one is in microampere or milliampere range. It's a very small current. Okay, then what type of relationship we can write between these 3 currents? Can't we write any equation like this? IE equals IB plus IC. Is it okay? IE is the outgoing current, but IB and IC are incoming current. Then total outgoing current should be equal to total incoming currents based on that relationship, we can write I equals to IB and IC. Still, we haven't introduced, still we haven't discussed anything new. So far, we have discussed all the things we know. Okay. Then what about the relationship between this? If you draw this one. This IB and IC. And this one may be IB is in microampere range. This may be in milliampere range. Okay. It's not all the time fixed, but I'm just showing you that to compare that one. What do you think about this two? Here I told you, when we forward bias this base emitter junction, then suddenly we can see this collector current is there. Current going through collector emitter. Then when we forward bias this diode, that is the forward voltage we have applied to this emitter junction, and because of that, forward current will be there. This base emitter junction, forward current will be there. That current is the IB current, base current. Then, okay, you have to understand that actually I'm not going to discuss that internal functionality for this operation. But anyway, when you increase IB proportionally, IC will be increased. Okay. When you increase IC proportionally, IC will be increased. Okay. We can draw this one like this. This. Like this. Then we can identify here, we have three regions. This region starting from 0 to this one is not linear. There is a curve here. And in this case here we have a linear region, and here after this point, again it's not proportionally increasing according to IB, and it may be having a different shape. It will be another case, another one. Then we say during this time IB is there. Sorry. Okay, this one, when IB increase, sorry, when IB increase this one, IC will be also increase. But see the slope. When you increase small amount of IB, as a result, you can see the large amount of IC will be increased. Then for the variation of small IB wave, for small IB variation, you can see large IC variation. Okay, then this is the graph between IC and IB. Okay, then here IC is proportional to IB. Then we have another type of equation we can say here. Then IC is proportional to IB, and then we can write IC is a certain kind of constant, times IB. And here we say IC is beta times IB. Then what is beta? Beta is IC divided by IB. We say this is DC current gain. Then beta is the DC current gain of the transistor. And this is the relationship we have to remember. Then beta is the actual, that beta is the DC current gain of the transistor. Yeah, I'll show you a practical data sheet for this one. Now we have a different name for this beta. It's the current DC current gain, or we say this one is it's HFE, the same meaning. Okay. Now this is the BC 107, BC 108 bipolar transistors, very common one. Here also we have to know about different the bipolar transistors. So I'll show you that. I'll explain that one again. Why they call this is bipolar transistors. Anyway, that this is transistor structure, emitter-based collector, and these are the electrical parameters. And this is the collector current, 0.2 ampere it can draw. And here this is the HFE, DC current gain. Okay. And for BC 107, DC current gain minimum 110, maximum 450. For BC 108, minimum current gain is 110, maximum 800. Okay. We'll check that a different transistor. Let's see this one. This is HFE. Minimum this one, maximum this one. BC 547, 547, 548 like that. And these are the, here why do we have the minimum value and maximum value? Because we make these transistors in bulk. And these transistors can have a range for this HFE, for this beta. It's not fixed value. Okay. Some transistors it's having this BC 547, 548, it's a fixed 120, maybe around 120. But this BC 547A is the fixed one, BC 547 no, generic one, it's 110 to 800, variation is the range is there. But you have to take the one transistor and measure the actual HFE value of that transistor. After that, you can use that. Okay. Then here, okay. Then now we know the characteristic curve of this one. The relationship between BB and IB, we already know about that one. That is a diode curve. And after that, we know this IC and IB curve. And another important curve is there. That is actually between we base to emitter junction and IC. This is an interesting one. I see maybe milliampere range. This is in volts. And when you consider the curve, you know that we up until 0.7 volts, you can increase VBE, but until 0.7 volts, transistor is not start conducting. After that, you can see IB is increasing. Because of that, as a result, IC is also increasing. But after certain time period, it's not going like that. Then again, this one, this region, you can see up to this point, the variation is linear. Okay. Up to this point that VB, until we provide VB 0.7 volt, transistor is not, the VBE junction is not forward biased. Because of that, transistor is not turned on. Because of that, we say in this region, transistor is in cutoff mode. Transistor is not turned on, it's cutoff mode. But this region, here to here, is a transistor is turned on and IB and IC relationship is linear. When IB is increasing, IC is also increasing proportional according to that beta value. Then we say this region is linear region. and we can consider this transistor is turned on. And beyond this region, beyond this point, transistor is not behaving like that. You can increase IB much more, but IC is not increasing according to the beta value. IC is slowly increasing, but it's not increasing very much rapidly like previous. And because of that, we say this region is saturate region. Okay. Now in the transistor, we have three regions: cutoff region, linear region, saturate region. Okay. Actually, we use this linear region for amplifiers. We use this cutoff and saturate regions for switching actions. Transistor is having two main applications. One is transistor we can use as a switch. For the switching actions, we use this transistor turn on mode and saturate mode. Saturate mode you can consider it's a fully on mode. But this linear region we use for transistor amplifiers. Okay, we'll come to this one later. But again, this cutoff, linear, set region, and this region we use for amplifier. But in these two regions, when combine these two regions, we can use this one to use transistor as a switch. For switch, you know that we need both ends, two different ends we know. We need one is turned off, the other one is fully on. Here in this active region is that this linear region is the active region. This one is active region. In this active region also you can consider transistor is on, but it's a linear mode. But when you go to the saturation mode, it's fully on. You can consider it as a fully on. This is in this region transistor is on. Here it's fully on. This is transistor off. Any question? Anything? Okay, another set of characteristic curves to be drawn, but I'll draw that one because it is essential to know that one. Now here, up to this point, what are the things we have used? What are the parameters? IB, we know the relationship between IB and IC. If you know IB and IC, we can find IE. But we know VB also. The relationship between VB and IB, we know it. When you turn on the base emitter junction, we know that IB is there. If you know the behavior of IB, you can say about IC also. But still we didn't use VCE. Now the relationship between VC and other parameters. What is VCE? VCE is this. Emitter to collector voltage. Okay, sometimes you may feel that this part may be a little bit boring. But anyhow, that we should know all these things. This is VCE, collector emitter voltage, and IC. Okay. Here that VC when IC is in that for different IBs, we'll have different type of things. So, okay. We will receive these type of curves for different IB values. Here, IB is 0. This is IB1. This is IB2. IB3. IB4. And different base currents. Okay. Here also we can identify these 3 regions. Up to this point, we can see this is cutoff mode. Cutoff mode means transistor is turned off. And here to here, here to here, this is this active region. And from this point, the other side, this is saturated region. Okay. In this linear region only we can operate this transistor. This linear region only, it obeys we have this relationship beta ICO IB. This relationship is valid only in this region. In switch off mode, there is no relationship, there is no validity here. You know the transistor is turned off. The saturate region is also, when you increase IB, proportionally IC will not be increased. Because of that, at that region also, that is equation is not valid. Okay, those are the basic parameters, basic fundamental things you should know about the transistor operations. All the time, what we have to do is, we have to forward bias base emitter junction, we have to reverse bias base collector junction, then transistor can work. After that, we can apply different modes. Modes means different voltages and different currents to that in a different manner. Then we can do different work. We can accept different functionality from the transistor circuit. Any question? Any question? If you don't have any question, then we have to go for the transistor applications. Then we will have some kind of questions we can discuss there. We can do some kind of calculations for various circuits. But before that, I think you may have, sometimes you may have a lot of questions, a lot of confusions, and a lot of explanations you need for different points. Anything? Okay, other thing that so far I have used NPN transistor here, but I didn't use PNP transistor for discussion. But in your scope and in examination also, we use only NPN transistors. But if you want to know about PNP transistors, but actually, whatever the thing we are doing for NPN transistors, you have to reverse the polarity, you have to reverse the voltages and all these things. Then it will be similarly applicable to PNP transistors also. But for the simplicity, is that you are doing this one first time. If you mix these PNP and NPN together, it will be a little bit harder to understand. Because of that, we discuss only about NPN transistors, but it's same for PNP transistors also. But here, for example, to forward bias the emitter-based junction, what we have to do here, we have to apply positive voltage to base and negative voltage to emitter. But in the PNP transistor, you have to reverse the polarity. Negative voltage to base and positive voltage to emitter. Likewise, we have to do all this. The current is here. Current is going from collector to emitter here. In this transistor, NPN transistor, you can see that arrowhead also pointing out that which direction current is going. In NPN transistor, current is going away from the transistor. In PNP transistor, you can see here, current is coming inside the transistor here. This is current flow coming in and going out. But this one, this direction. From collector to emitter, from emitter to collector, current, this is emitter and collector. This is collector to emitter. Okay. Now, we can try this question. Okay. Now here we have a transistor circuit, something like this. This is 0 volts terminal, and here we have resistor. This is RL, and this is plus VCC collector voltage. and this is RB. Okay, you know that RB is 500K. This is 500K. This RL is 2.2K kilo ohm, and this voltage is plus 12 volts. Now you have to find RB. Okay, you can find it. Sometimes that you can answer this one, maybe, but for different HFE values, for 200 HFE and 400 HFE, you can calculate IC and VC values. Okay, shall you do this one? Shall you spend a couple of minutes? HFE is 200 one time, and different times 400. Okay, for 200 you can calculate IC, and for 400 also you can calculate IC, and you can calculate respective VC values also. Okay, you know how to turn on transistor. Apply those conditions here. Assuming that you can find these values. Okay. Maybe it's not, but you can answer these two. A and C you can definitely answer, but we can discuss B. Okay, take a couple of minutes and find this. Okay, how can we find these things? Okay, first of all, that what we should know that to turn on transistor, we have to forward bias this emitter-based junction. To forward bias this emitter-based junction, we have to apply 0.7 volts across base to emitter junction. Okay, then here we have 0.7 volts. Then across RB, what is the voltage? It should be, supply voltage is 12 volts. Then here we have 11.3 volts. With that, we can find IB. RB equals IB into RB. Okay, because this is the base current, and as a result, here we have collector current. Then this is the VCE voltage we want to find. VCE. VCE. Okay. First of all, that shall we try to find IB? Then here IB. RB 11.3 volts. IB we don't know. RB is 500K. Okay. Yes, 500K. Then IB equals it's 22 microampere. IB is 22 microampere. The next one, what is the purpose of RB? Actually, what is the purpose of RB? RB provides the necessary voltage to base terminal to turn on the transistor. Okay. C see that we have two HFE values. First HFE is 200 and 400. 200, and for 200 we have IB value. Then we have to calculate IC value. IC is HFE times IB is 200. IB is 22 microampere. Then it's 4.4 milliamp. When no, it's okay that we can see that HFE is equal to beta. Doesn't matter. Beta 200 or beta 400, you can take like that also. Doesn't matter. HFE is also the different name for beta. Then IC equal 400 times 22 microampere. Is it okay? Then the second question means that this one, type part C. Okay, here that part B, RB provides the necessary voltage to base to turn on the transistor. Actually, that without having this RB, you know that here that we have to provide 0.7 volts to base emitter junction to turn on the transistor. Okay, but if you provide more than 0.7 volts, then base emitter junction will be damaged. Base emitter junction will be damaged means the entire transistor will be damaged. No use of that transistor after that. Then because at base to base that we have to provide a current in a very low range. It may be in microampere range in this case. Okay, to reduce that current to that microampere range and take the power from positive input, then we have to have this arrangement. Okay, then this RB takes positive voltage from this 12 volts power supply and it reduces this voltage across the resistor and it provides the controlled current to the base terminal in order to have 0.7 volts across the base emitter junction. Okay. Then without having RB, we cannot turn on transistor safely. We can turn on transistor providing any voltage here, any positive voltage to base terminal. But we have to maintain this forward bias base emitter junction. At the same time, we have to reverse bias base collector junction nodes. That's why this two different transistor values for this 500K transistor, when you put 500K resistor here, this base terminal voltage value will be less than collector terminal voltage value. Why? Here for the collector, we have put 2.2K resistor. It compared to 500K, it's very, very low one. Then at the collector terminal, we have higher voltage than base terminal. Then we are maintaining this forward bias emitter-based junction and reverse bias base collector junction rule. Without having that one, we cannot turn on the transistor. That's why we say RB provides the necessary voltage to base to turn on the transistor. Or maybe you can, in addition to that, you can say that it's providing the control current to the base terminal to prevent the transistor being damaged. Is it okay? Okay. Okay with this one, this calculation. Now we can go for transistor applications. Transistor applications. The first application is as a switch. We can use transistor as a switch. Okay. Wait a moment that. Okay, this part cannot be saved. Otherwise, maybe that you can see, I think this document at least. Now here, the previous part, I think I will try to recover later on, but this one we can continue from this point. The transistor applications as a switch. But you may remember this characteristic curve we discussed earlier. Here, this one, VBE IC curve, and this one, VB IC curve, and you may remember that to turn on diode, we have to apply 0.7 volts. But here we have to have some kind of clarification, but hereafter we use that points. This one, you know that here I told you that in the transistor we have on mode and fully on mode. Okay, because of that, we say here at this point, this is 0.6 volts, and this is 0.7 volts. Okay. When you change 0.6 to 0.7 volt at the emitter-based PN junction, then it's going from on mode to fully on mode. Okay. Then when you apply 0.7 volt to the transistor, it will be switched to fully on mode from on mode. This 0.1 volts difference is enough to go between these two things. And here, then after putting the transistor into saturate mode, we have to remember this one when the transistor in saturate mode. Okay. VCE is into 0.2. Okay. What is that? When transistor is into saturate mode, this voltage will be 0.2. Okay. Then in the switching mode, when we use transistor as a switch, we are going in between these two modes. What are those modes? We are going in between cutoff mode and saturate mode. Then this here as a switch. In switching application, we put transistor into cutoff mode one time, and we will bring back to it to saturate mode. And we are going in between the cutoff mode and saturate mode when transistor working as a switch. Okay. Then to put this one into cutoff mode, what we have to do is and we are applying when V in is 0 volts, what will happen? And this is IB, and this is IC. When V in is 0 volts, then this VB junction, there is no voltage across VBE. Then as a result, VB is 0 volts. Then as a result, junction is not turned on. Then IB is 0. Because of that IB is 0. IC also 0. Okay. Because of that, ICE is also 0. VCE is plus VCC. See that, is it okay with you? When V in is 0 volts, and here we have applied 0 volts, then no voltage. Because of that, this junction has not received any voltage. Because of that, this junction is not turned on. Then there is no forward current. Forward current means IB current is 0. If IB current is 0, you know that in the external path, this IC collector current is not flowing through the transistor. When IC is 0, then across this resistor, there is no current flow. There is no current flow means, and this side voltage will come to the collector point. Then because of that, VCE is VCC. Okay. Then the other point, when V in is larger than 0 volts, for example, we say it's larger than maybe 1 volt is also enough. For example, in this case, shall we take more nearly equal to plus VCC, it's a higher voltage. Because of that, then VBE, we have to make sure that then VBE is 0.7 volts. When VBE is 0.7 volt means we have IB current. IB is greater than 0. With that IB, as a result, IC is greater than 0, which is not greater than 0. And because of this, we put transistor into saturate region. And IC is greater current, then when transistor is in saturate mode, as a result, VCE is 0.2 volts, or we can think about it 0 volts. Because transistor is in saturate mode, because of that, VC is 0.2. Okay, then what will happen? Across this resistor, the full VCC voltage will be appear because this is 0. VC is 0, because of that, then this VRL, this VRL will be plus VCC. Okay, we will not write that one here. As a result, VRL is plus VCC. Okay, real calculation will not be this much of difficult. Actually, this is not difficult. This is a very logical thing. We are following step by step. If you go through this one step by step, you will easily understand this one. But sometimes that if you are seeing this one first time, you may think that this may be real difficult one. But actually these things are not difficult. We are going step by step logically. We have a logical flow. If you understand this logic well, then we can come to the solution very easy. Okay. But when you come to the real calculation, real problem, this theoretical expression may be a little bit difficult than the calculations, because when we do the calculation, we have real values. But here we use symbols. Is it okay with this? Okay, then we can draw a real application here. Think about this very simple application. Now here we have 12-volt supply, and assume that you want to turn on electrical bulb. This bulb may be 12 volts bulb, and we are putting transistor here. To turn on this bulb. Here we have RB resistor. Then beta of this transistor may be 100. We can take it as 100. Then this current of this 12 volts bulb, it may be 200 milliampere. We need that current. Okay. Then if it is 200 milliampere, we can find IB. Normally, in the linear region, this equation is valid. IC equals beta times IB. Now we have to find IB here. IB is IC divided by beta. IC is 200 milliampere. Beta is 100. And as a result, IB will be 2 milliampere. And this is IB, and this is VBE. To put that one into saturate mode, it should be 0.7 volts. Then definitely to put that one into saturate mode, This is 2 milliampere. Then we have to keep beta. Then real IB should be greater than 2 milliamp. Then if you put that condition there, in the saturated region, you can see IC is less than beta times IB. Why? To make sure that transistor is, we are putting into saturated mode, we put little bit more current to IB. Need to make sure that here we have 0.7 volts. Okay. Then to have 0.7 volts, then IB, nearly we can calculate it as 2 milliampere. Then if it is 2 milliampere, then here we can see that this is the V in voltage, assuming that this is 5 volts. Then this is 0.7 volts, and across the resistor we have then 4.3 volts. Then we can find RB here. RB equals 4.3 volts divided by 2 milliampere, but you have to remember that IB should be more than 2 milliampere, but okay, here the marginal value we can find this way. 4.3 volts. 4.3 divided by 0.002. Then on theoretical calculation, it's coming 200, 150 ohms, but in practical case, we don't have 200, 150 ohm resistor, and we put this one as 2000. Then this is 2K ohm resistor. We put little bit less resistor value to make sure that more current is going towards base terminal. Okay. When you put RB as 2K 2 ohms, then here we have this current, and the output current 200 milliampere will be there. And when we okay, now having this arrangement, when V in is 0 volts, what will happen? Then IB 0, then IC 0, then because of that IC 0 means this bulb is off. Okay. When V in is plus 5 volts, IB is 2 milliampere, then IC is greater than 200 milliampere, so similar, then bulb is on. But you can see this one. I put this greater than or equal symbol here. Why? You know that when we compare, when we consider this graph here, See here, this one, or maybe this one also. You can increase VB much more, but IC is not increasing relatively to that one. And same for IB, IC also. Here, after coming to into the saturate mode, the IC is not increasing much more. Okay, then therefore we can say IC is more closely, it's around 200 million. Then when we have this arrangement, you can consider this as a switch. Then transistor is working as a switch. When we provide positive voltage, you can turn on it and you can turn on the bulb. And when you provide 0 volts there, you can turn off the transistor. Turning off the transistor means you can turn off the bulb. Then your transistor has been working as a switch. Is it okay? During this time, you have to remember that now here transistor is in saturate mode. Because of that, VC is very much close to 0 volts. Then the voltage across the bulb. Then voltage here, when the transistor is in saturate mode, this VC is 0 volts. Then across the bulb, you can see 12 volts will be applied. Then there is no voltage drop across the transistor. Then full voltage will be applied across the bulb. Then no problem coming from the transistor. Is it okay? Okay, if it is okay, then we can stop class now. And thank you very much for your patience and the support. Today that we have 2 sessions. I think now we have to cover up. The bulb has maximum intensity at saturated mode. Yes. Actually, we have to make sure that we are operating transistors in 2 modes only. We turn off the transistor without providing voltage to the input terminal, and we provide 5 volts there. Then we push the transistor into saturate mode. We have to make sure that transistor is operating only on these 2 modes, these 2 ends. If you put the transistor into active region, then we will be in trouble. Transistor across the transistor at VCE, you will have some kind of voltage. And across the transistor, voltage is generated. Transistor will be getting heated, and then transistor will be damaged. Because of that, when we use transistor as a switch, we have to make sure that they are operating either cutoff mode or saturate mode. Okay, you can take these things and maybe I'll put these videos without having any delay, maybe today or tomorrow. Then you can refer those things because we don't have much more time. Then you have to refer these things again and again. And if you have any kind of problem, we have to discuss those things. Anyhow, that within this week, we have to finish everything. And we have to do 4 more classes. I'll have some time thoughts and I'll discuss with Chamat. And Chamat will let you know the time slots of these things. Anyhow, that before this weekend, we have to have all these 4 things finished. During the weekend, we can have tutorial session. Okay, then thank you very much for your support, for your patience to wait until this much of time. Okay, we'll meet next time again. Until that, have a nice time. Thank you very much.
Thank you, sir.
Thank you, sir.